Hello and welcome to Wednesday's edition of Cracking the Cryptic. And today we're going to be looking at a puzzle by Phistomefel. I mean, I've had to do this. He's released a number of puzzles on Logic Masters Germany, and we're getting behind if we don't keep up. So this one he calls the Cloverleaf, and I think you can see why if I highlight the given cages here. I try not to do this without misclicking. You will see that we seem to have the outline of a four-leaf clover. And some interesting cages as well. This is normal killer Sudoku today, so we'll check this out in a moment. Before we get started, just to say, if you are a patron of the channel, then over on Patreon right now we have the solution video to the Tour de France bonus puzzles that we released at the start of the month, so do check those out. Now let's get back to this. I'm a little bit worried about doing this puzzle, I have to say, because Phistomefel describes this as his tribute to ahaupt. Now, we have covered 2 or 3 puzzles by ahaupt on the channel. They have been universally, monstrously hard and utterly brilliant. In fact, Cracking the Cryptic, the movie, is one of the longest solves we've ever done, and actually one of the best solves I think I've ever done. It's certainly one of the hardest puzzles I've ever tried to solve or have solved. So when Phistomefel, who's one of the world's great constructors and is not known for his easier puzzles, decides he's going to make something as a tribute to ahaupt, I feel the right to be quite scared. Yeah, as I say, normal killer Sudoku though, so what we've got to do, for example, this cage, we've got the digits in the cage have to sum to 11. You can't repeat a digit in a cage, so you can see that there's a couple of 45 cages. Which basically means that they must contain the digits 1 to 9 in some order, because 1 to 9, if you add them up, you get 45. And that's all we know. So do have a go. The way to play, as usual, is to click the link under the video, and that means it's time for me to have a go. Let's get cracking. And if you've been following the channel, you'll know the last couple of Phistomefel puzzles that we've solved, I have got through them, but you know, I've had to throw everything bar the kitchen sink at them, and often haven't done them in the way that Phistomefel intended them to be done, so I will try and do better today. Now, as I'm scanning the grid though, I'm not seeing a great deal of help. I mean, I know there must be a 9 in a 22 cage, but that is not going to solve the puzzle for us. There are very few cages here that are actually... I mean, there are some cages we can get down to just 2 options. 5 has got to be 1, 4 or 2, 3. 15 has got to be 7, 8 or 6, 9. 6 has got to be 1, 5 or 2, 4. But that's it. Good grief. So we're probably going to have to do some geometric gymnastics to kick off. How on earth do we do this? Well, yeah, I mean, I can see, as I'm sure we can all see, that these rows and these columns have lots of cages in them. So let's stare at that for a while and see if inspiration strikes. Problem is, there's so many cells sticking out or overlapping in this arrangement that it seems hard for me to believe this is actually going to yield anything. Let me colour it in. Maybe that will provide the inspiration. Let me stare at it again. What have we got? So obviously, I mean, each row here is adding to 45. Each column is adding to 45 because it will contain the digits from 1 to 9. But I can't just say that, you know, this plus this is 90, because that's double counting this cell, the value of which I don't know. Also, the 45s, although they do include a lot of the purple region, they have cells sticking out, which is not helpful. I'll tell you one thing I could do, actually. Let's get rid of the overlapping problem. I can get rid of the overlapping problem by highlighting more cells in purple. Let's do it that way. Yeah, this gets me a relationship. It gets me a relationship between the outside cells from the 45 and this cell, I think. let me explain what I mean there. So we've got the purple region. We know the sum of the purple region because it's 5 complete 3x3 boxes of the Sudoku. So it's 5 lots of 45, which is 225. So the purple adds up to 225. But I've got some cages that are entirely or almost entirely overlapping with the purple region. So if we were to add up those squares, we would get 30. These ones we get... that's interesting. That's these ones down here add up to 50. So the orange squares now add up to 80. We've got 2 lots of 45 on top of that, but that needs correcting for slightly. So that's another 90, but that's including these cells here, which I'll need to miss out again. So I've now got 90 plus 80. That's 170. But I've included too many cells in that, and then I can, yeah. If we look at column 5 and row 5 of the grid, what do these two, or what do the orange squares add up to? They add up to 90 minus the value of this square, because that will be counted twice. I know that's 45 individually, that's 45 individually. So I'm going to have 90 less whatever we include in there, because I mustn't count that twice. So what does all this mean? So it means we've got... So if we start with the purple squares, we've got 225. And that's going to be equal to 80. So we've got, sorry about this, 80, 170... minus these cells. I don't want to include those cells because they shouldn't be included in the purple. So minus these cells. Oh no, I've got to add in another 90 as well, haven't I? 90 minus this one. So what's that? Gosh, 260 minus this one. Okay, so we've now got a relationship. We've got 225 is equal to 260 minus these highlighted cells in the grid. In other words, the highlighted cells in the grid add up to 35. Now, that is that interesting? It would be. I mean, the one way that strikes me as interesting is that 5 cells to make 35. If we couldn't repeat a digit, they would all have to be different. So if I did know that the red cells all had to be different numbers, we would have something quite interesting here. So let's think about that. Is it necessarily? It's obviously necessarily the case these are different digits, and then whatever these digits are won't appear in those cells. But there's nothing there that's telling me that that can't be the same digit as that, or even that this can't be the same digit as this. At least I don't think there is. I think I've led you all on a big wild goose chase here. I don't think this is what we're meant to do. Okay, alright, we've got to get rid of this. I think this is not right. I'll leave the red ones shaded. I'll make them green instead, so it's a bit less offensive. So the greens add up to 35. That's something that we can use if we get the opportunity. Right, so what on earth do I do if it's not that? I mean, there are some things I notice but don't really understand how to use. I mean, those digits are all relatively small. These digits are all relatively high. I mean, these digits are incredibly high. But I don't. But even if they are incredibly high, what does it mean? That's the question. I don't know what it means. Can we use... Maybe I shouldn't be using so many rows. Maybe if I just look at one row. So, okay, let's look at one row. I mean, this is a slightly... I don't think this is going to work, but I will just check it. So we've got 13 plus 6 there. That's 19. Plus 45. That's 64. So now I know that this row here, this whole row, I'll make it purple, adds up to 45. So if we want to find a relationship here, we can say that 45 is equal to 64 minus all these squares. They'd all have to be removed from that equation, and plus that square, whatever that square happens to be. So, I mean, that's a little bit interesting, only that the yellow squares here have to all be different digits because they're part of the same cage. So the minimum I could make the yellow squares would be 15. Yeah, but the problem is, I mean, this could be anything, absolutely anything, and it would still be absolutely easy to make those squares add up to it. Unless I'm missing a trick there, but there just doesn't seem to be enough play, because, you know, 64 plus a number, let's make that number 6 for the sake of exposition. We've got 70, so I need these 5 cells to add up to 25. Well, that's completely straightforward. And obviously, if I make that 1, then we'd be saying these 5 squares have to add up to 20. Again, that's totally straightforward. No, this is not right. This is not right either. Sorry. This sometimes happens with live solving. I mean, I've got these 9s here. Let's not forget these 9s. That was important. I'll try it again down here. These are bigger, so this might be better. We've got... right, let's make that purple. What have we got? We've got 60, 81. So we've got 45 is equal to 81 minus these cells, all of those, plus this square. Let's make that one red. Oh no, I didn't want to do that. I want those staying purple. So 45 is equal to 81 plus this square minus all of the... I'm going to have to change the colour of these greens. Let's do it like that. So, oh no, and that one as well. That one's got to be included. Nearly forgot that one. That's sticking out of the bottom of the 21 cage. So we've got... So I've got 45 is equal to 81 plus this. So 36 plus this is equal to the sum of the blue. So the blues are equal to 36 plus the red. The blues are equal to 36 plus the red. Is that useful? That might be useful. That's better. It's definitely better than the this row. Yeah, it is better, and one of the reasons it's better is I've got a 14 cage down here and a 20 cage here, which does actually put some limits on how high I can make these digits. So for example, if we look at those two, what's the absolutely highest I could make those two digits? Well, it's 15. If I make them any higher than 15, these 5 cells together will add up to more than 35, and that's impossible, because 5, 6, 7, 8, and 9 add up to 35. So these two can't be higher than 15, these two here. Now these, it's a little bit harder to see, but we've got a 14 cage in here. So what's the minimum? What's the maximum, I should say? I could make 6 cells if we're using different digits. Well, it's 39, I think, isn't it? Because I'll be missing 1, 2, and 3. So the maximum for these squares on this side is 25. Okay, well this is something. This is something. If these can't be greater than 25 and these can't be greater than 15, there's no way together they can be greater than 40. But we know they are equal to 36 plus whatever I put in that cell. So if I put a 5 in this cell, these blues are impossible to fill because they'd have to add up to 41, and we've just shown that's impossible. So this is a start. It's not much of a start, but it is a start. This has to be 1, 2, 3 or 4. Now, oh yes, now this is getting more interesting now, because where do we put? Yeah, this is gorgeous. This is gorgeous. Okay, so the key thing I think we can recognize about the red cell is whatever I put into it, where does it appear in the blue, in box 8 here? Well, you can see no matter whether this is 1, 2, 3 or 4, it can't go in the 14 cage. That would be impossible. So it must go into a blue cell. So if we revisit our equation, we said that the blue cells are equal to 36 plus the red cell. But now we can go further than that. We can say some subset of the blue cells, the 5 of the blue cells, because one of these will have to be a 1, 2, 3 or 4, 5 of the blue cells have to add up to 36. Now, I'm just wondering if I can force those 35 of the blue cells have to add up to 36. No, this is perfect, isn't it? This is perfect. Because if 5 of the blue cells have to add up to 36 and those two can't add up to more than 15, 3 of these 4 blue cells in this one have to add up to 21. But if 3 of them add to 21, I add the 14 to the 21 and I get 35, which means that 5 of these cells are absolute maximums and the other is the 1, 2, 3 or 4 that mirrors this one, and these do have to add up to 15. That is progress. So we get 6, 9 or 7, 8 into these two cells. These 5 cells together add up to 35, so okay. And whatever I put in here has to appear in one of these blue the blue cells. Now, oh, it can go there. No, it can't. Oh, now I was hoping I would be able to rule out whatever I put in this cell from this square, because obviously 1, 2 and 3 can't go into a 21 cage, but 4 can. But if this is 4, look, it breaks the 15 cage, because now we'd have to put 8, 9 in there, and there would be we can't put 8, 7 or 6, 9 in this 15 cage. So this square here is not the mirror of this square. Which means, let's just get rid of it's getting rid of the colour. Gets rid of I want the colour back. And I want to, so this square, I can't really notate this properly, but it's going to have, one of these squares has to be whatever that square is, but I don't know which one. I'll put it in the middle. So that square will be our designated mirror for this square. The other 3 squares have to add up to 21. So the 14 cage is either 5, 9 or 6, 8. And the other cells here have to be 5, 6, 7, 8 and 9, apart from whichever is the mirror for this one, which will be itself, but it will go in one of those 3 squares. So that means these 3 squares have to be from the nut digits 1, 2, 3 and 4. because obviously 5, 6, 7, 8 and 9 are absorbed in these 6 cells along with the 1 mirror. Sorry, I know I'm being slow, but at least I am discovering things now. This is better. Okay, what does it mean? We now know these two add up to 15. That must be important. Oh, it would be nice if those two can't add up to 15, because then we would know that whatever we put in there had to mirror in here. No, this could be 6, this could be 7 and 8, that could be 6 and 9, that works. Bother. Okay. Ah, I've got something. I've got something. No, I haven't got it. Ah! No, I was misreading my pencil marks there as suggesting that we had all 5 digits, all 5 high digits in these cells, but we don't, because one of them is going to be displaced by this one, so it's my pencil marks giving me trouble there. Maybe I just have to start pencil marking in things here. So, what on earth am I meant to do next? Oh, if I know those add up to 15, they are part of my original green cells, look. So, I now know those 3 squares have to add up to 20. I have got no clue what to do here. Sorry. Maybe this 21 cage is limited. Let's have a look at that. If this was 5, these two would have to add up to 16. They'd have to be 7 and 9. Ah, yeah, there we go. They are limited. Well, the 21 cage isn't limited, but the 15 cage would be impossible. If this is 5, you can't make this work, because 7, 8 and 6, 9 are impossible. So that is progress. So this square can't be 5. Well, can it be 6? Maybe it can't be. Maybe there are things it can't be. I think I've looked at 6 though, because now this has to add to 15 without being 6, 9. That can be 7, 8. This can be 6, 9. That works fine. That then would be 5, 9 down here. 5, 9. This would have to be from... Oh no, this would have to have 7 and 8 in it. 6, 9. Ah, no. Oh, good grief. Right, okay, Phistomefel. I think actually probably the first 23 minutes of this solve might have been a complete red herring, because I've just noticed something quite incredible about this little corner. If this is a 6, you get a 6, 9 pair in these 3 cells, and you get a 6, 9 pair in those 3 cells. Why, we might say, is that interesting? Well, look. Where does 6, 9 go in this 45 cage now? Because of this 6, 9, it can't go in those, and because of this 6, 9, it can't go in those. So the only places that could be the 6, 9 are these two. But look, it does exactly the same for this one. This 6, 9 rules out those ones, this 6, 9 rules out those ones, so you get 6, 9 pairs there, and there. Now obviously this is predicated on this being a 6, but this... I wonder if this is why these digits are so high. It's because you always force the same things into these cells. So I'm going to look at this now with much more care. So let's do it. So what we can say now is we've looked at 6, we haven't looked at 7. So if this was 7, now maybe this is in... If this is 7, this has to add to 14. Ah, so this can't be 6, 9, because that would rule out 6, 8 and 5, 9. So this has to be 7, 8 this time. This now has to be 5 and 9. Now this is very clever. So now this 16 can't be 5, 9 and would have to be 6, 8. And this time, look, it's the same again, but now instead of 6, 9 working, it's 7, 8 working. So with 6, we ended up with 6 9s here and here and here. With 7, we end up with 7 8s here, here, here and here. This is very, I mean, it's amazing. How on earth do you discover something like this? It's completely baffling. So let's try 8. If this is 8, this now has to be 5, 9. This has to add up to 13, which looks... okay, this having to add up to 13 means this can't be 6, 9 this time, because if it's 6, 9, you couldn't make 13, because 8, 5, 4, 9 and 7, 6 would be unavailable. So this now has to add up to 13. So this is not 6, 9. This has to be 7, 8. This has to be 4, 9, and there's 9s here. So the 9 would go here, the 4 would go here, and we get... This time we get 9 8s pushed into the boundaries. Oh, no, that won't work. 9 8 won't work up here. There's a 19 cage. And that would make those cells add up to 36, which is too high for 5 cells. So I don't think 8 is possible. Oh no, and it's even worse down here. There's a 20 cage. So 8, 9... which is 17 obviously, plus 20 is 37, breaks this. This is not 8, definitively. Okay, good. Let's go back to this point, colour that in again. So can this be 9? If it's not 9, we're happy days. We know that these are 15s. Now 9, put 6, 8 below it. It means these two squares add up to 12, which means this can't be 7 and 8, because that would remove all ways of getting to 12 in this domino. So this time this is 6, 9. These two have to be... Oh, these have got options this time, have they? They have... This could either be 5, 7 or 4, 8, but it doesn't matter for our purposes, because look, we've got a 6, 9 pair here, a 6, 9 pair here. So with 9, you end up with 6, 9 pairs. Now, this is going to give us this square. It's going to give us this square, because what we've worked out is that no matter what we put in this square here, whether this square is 6, 7 or 9, they are the only valid options. Whether this square is 6, 7 or 9, you always end up with these two cells adding to 15 and these two cells adding to 15, and they're always the same. So if this was a 7, 8, this will be a 7, 8. And why does this give us this cell? Well, right at the start, we proved that those 5 cells added up to 35. So if these 4 cells together add up to 30, I get a 5 in the grid. Happy days. That's taken me a long time. Now that can't be 5. That can't be 1. Those have got to be 5, 6, 8 or 9. What does this mean? That's the next question. What does it mean? The answer is I don't know. I feel I'm close to getting some sort of grip on this puzzle, but not quite close enough. I mean, this 5 ought to be really helpful. How is it helpful? That's the question. I just don't know. Is there something going on with high and low digits? I'm just looking here. I've got a 5 cage. So 5 cage can only contain small digits. By small I mean under 5. This box here has got lots of yeah, okay, look, maybe that's how we should approach this. I've got 4 low digits now. I've got, in fact, a quadruple on 1, 2, 3 and 4. So this square's got to be 5, 6, 7, 8 or 9. Now have we got that anywhere else? The answer is of course no. I suppose that those two have got to add up to 15 as well. If these add up to 15 and this adds up to 19, these 5 cells together add up to 34, and there's only one way of doing that. That's 4, 6, 7, 8 and 9. So we must have this. We must have a quintuple here, which means these squares are 1, 2, 3 and 5. Okay. Now, what can we do next? Answers on a postcard, please. I don't know. Ah, I've got something. I've got something. Let's look at those 2 squares. Those 2 squares add up to 15, but they don't make an appearance in any of those 4 cells in column 4 because they're in the same box. So whatever these 2 digits are have to appear in these 5 cells of column 4. Now these are big digits. These are 6, 7, 8 and 9. So I can't put them, well, obviously I can't put them both in an 11 cage because we know these 2 cells add up to 15. That would definitely break the 11 cage. So one of these digits has to go here for certain. But perhaps more interestingly, one of them has got to be in the 11 cage. And if one of them is in the 11 cage, it can't be a 9. Because you can't put 2 1s alongside it. So there is no 9 in this cage. So this 11 cage contains a 6, 7 or an 8. Right. Got it. Got it. If it contains a 6, 7 or an 8, it doesn't contain a 5. So this 5, where does 5 go in box 2? It must go on the right hand side. Which means 5 must be in one of these cells. And why does this matter? It tells us what our 14 cage is. Our 14 cage is not 5, 9. It must be 6, 8. So there's no 6, 8 down this side. There's no 6 in the 21 now. Oh, this is beautiful. This is beautiful. So now we can carry on with this logic, I think. Because if we know there's a 5 in one of these cells in this 45 cage, and we do know that, and there's a 5 here, then there must be a 5 in one of those 3 cells. Now, if there's a 5 in one of these 3 cells, and you combine it with this 5, where do we put 5 in that run of cells? It can't go in the 15 cage. I think that has to be a 5. Now that means there's no 5 up there. This square now, this has to be a 7, 9 pair, so we get another digit, well, another pair. And okay, if we look down here now, we've got 1, 2, 3, 4 and 5 at the bottom there. So those squares have got to be 6, 7, 8, 9 in some order. Okay, that's good, but it's not... We haven't cracked the puzzle yet, have we? Unfortunately. Maybe. Okay, I've got something. I'm not sure if it's important, but I've got something. Let's carry on thinking about high and low digits on column 4. So, I know one of these cells is my mirror of this. So one of these cells is a 1, 2, 3 or 4. This cell is a low digit. Now the 11 cage has got a 6, 7 or an 8 in it. So the other two cells have to be low digits. They have to be either 1s, 2s, 3s or 4s, because if we make one of them a 5, we're going to have at least 11 in 2 cells, which obviously is going to break the cage once I don't put 0 in that one. So there are 2 low digits in the 11 cage, 3 low digits here, and the mirror cell here, whichever one of these is low, is the 4th low digit. Now that means the rest of this column is high digits. In particular, this square must be a high digit. So let's make that high and see if that tells us anything new. Yeah, that's quite cool. That's quite cool because now I can see a few things. Firstly, I can see I've got all my high digits located in box 5. So these two must be low digits. And look at row 6 of the grid. These two squares here are high, definitely, because they're either 6, 9 or 7, 8. So if we look along here, 1, 2, 3, 4, 5. In fact, that's quite interesting. As those two add up to 15, these two must add up to 15. Which means this square here is not 7 or 9. This is 6 or 8. But that wasn't actually what I was thinking about there. What I was thinking about is that these are all high digits. So the rest of this row are low digits. I've got no idea, by the way, if this is... Sometimes when you solve Phistomefel puzzles, you sort of feel like you're seeing, you know, his genius is revealed to you and you're like awed by it. Whereas today, I feel like the genius is just too clever for me, and I'm sort of finding my way along this path without understanding quite how these clover leaves fit together. Yeah, look at. I have something quite nice here, I think. Column 3. I've got 3 low digits. Yeah, this is good. This is good. I'm going to get this cell. So, if this cell is a low digit, we will have 4 low digits in this column. And that will mean this domino here will have to contain high digits. Well, this is a 22 cage, so that's got high digits in it. You can't put a 4 in a 22 cage. It's impossible. So the total quota of high digits in box 1 will be taken up in those squares. How do you then fill a 10 cage? You can't. You need 1 high digit in a 10 cage. Now why is this so important? Well, it means that this can't be a low digit. This has to be a 5. And that gives us a bit more. It gives us 2 more digits. There's no 5 in that cage now. This 1 allows us to do some eliminating. So there's no 1 in this square, so there's no 1 in the mirror down here now. Right, okay, this is good. No, this is good. I'm sure it's important. I just don't know how yet. Oh, please don't. That must be important. I had to work so hard for it. 1 must be in one of those cells now. So 1 must be in one of these cells. Oh, it is important. The reason it's important, I've been looking at the rows. I'm now looking at the columns. The 11 cage. If the 11 cage can't contain a 1, what is the high digit in the 11 cage? It can't be 7, which would need a 1 and a 3. It can't be 8, which would need a 1 and a 2. So this cell... Yeah, this is forced. This whole cage is forced. It's got to have a 6 in it, and it can't have a 1, 4 alongside it. So this cage is 2, 3, 6, and we are cooking with gas, maybe. Ah, yeah, where does 6 go? In column 5 of the grid. It's naked there. This 6 gives us this 8. We know these two added up to 15, so this must be 7, this must be 9. No 9 at the bottom of this cage. Oh! Yeah, look. In fact, once we've got an 8 in the 45 cage, we know those two add up to 15, so they can't be 7 and 8. They are 6 and 9. That's another reason there's no 9 here. This 15 cage is obviously 6 and 9 as well. And indeed, we know from our logic earlier, we've now got 6-9 pair here, 6-9 pair here. So the 6-9 pair in this 45 cage, sorry, the 15 pair up here is also 6 and 9, which means we remove 6 and 9 from the 19 cage. This square can't... Oh, that square's a naked single, that's a 9. This must be a 4-9 pair in our 13 cage, because we need to put the 9 in the box somewhere. If there's a 4 there, there's no 4 down there. So this becomes 1, 2, and 3. This square becomes a 4. Now, if this is a 4, it has a mirror down here. So we now know this is a 4, 5, 7 triple. Let's put that in, which we actually knew anyway if I'd concentrated on the column, but I wasn't concentrating on it. Sorry. Okay. Suddenly we get a little bit of progress. And it's probably about to stop again. Now, those 3 squares here have got to be, from this box, you can see they've got to be 1, 4, and 5. This row still needs 2, 3, 7, and 8 into those squares. There's got to be a 4 in one of these cells, but we don't know where. This 9 tells me the 6, 9. We get the 6 9s on this side, look. Let's remove 6 and 9 from the 20 cage. 8s, look, are locked into row 8 and 9 of the grid in 2 different boxes. So we now know that 8 in row 7 has got to be in one of those 3 positions. Still don't know whether this 22 cage is 967 or 958. At least I don't think we know that. What do we know now? 9's at the bottom. 9's have got to be in one of those 3 cells. Can we put a 9 in this? No! Oh, this is good. We can't put a 9 in the 13 cage. Why not? Because if we did, it would have to have a 1 and a 3 with it. And that is not a problem for the 13 cage, but it's a mighty problem for the poor old 5 cage, because if you can't use 1 and 3, you can't make 5 in 2 cells. So the 9 is not there. The 9 is here, which gives us the 9, 6 at the top, look. Which gives us the 9, 6 in this 15 cage. Ah, now look, 6. 6s. Where do 6s go in the grid? In this box, only in one position. And importantly, in the 13 cage. So the 13 cage doesn't have an 8 in it. This 6 gives me the 6 and the 8. That gives me the 8 here. This square's a 4. Keep going, keep going. Bother. Oh, we were on a run then, and now it's ended. This can't be 6 or 9. Or 8, actually. It's a 5, 7 pair here. This 13 cage has got a 6 in it, so these add up to 7 without using 1, 6. So this is 2, 5, or 3, 4. Oh, it's clever. It's very clever. Why is it clever? Well, this 5 cage not only disambiguated where the 9 went in this box, it's just disambiguated, well, the 13 cage and the 5 interaction has done all sorts of things, because if we need a 2 or a 3, and we do, to make 7 in this domino, we can't use 2 and 3 in the 5 cage. So this must be a 1-4 pair. And once it's a 1-4 pair, this can't be a 3-4 pair, it's a 2-5 pair. And that means this square's a 7, and this square's a 5, and this square's a 7. And here we go again. That can't be 4. That can't be 7. Look up there. That can't be 7. So if there's a 7 in one of these two cells, and there is, where does 7 go in row 4? It can only go in that position. So I will take that. 8 must be in this domino. Okay. This is 2, 5. So we remove 2 and 5 from that square. Remove 2 from this square. We still don't quite know what the composition of those 3 cells is, at least I don't know it. These two here have got to be 3 and 8 by the looks of things, so let's put that in case it's helpful. It does limit 3, or remove 3 from a couple of places. Now there must be a 4 in one of those two squares, so there's no 4 here. This 5-7 pair is pointing at the 2-5 pair over there, so we do get some more digits. Good. This 2 knocks a 2 out of those two squares. So we've got several 1-3s in the grid. And those 3 squares. We do know what those 3 squares are. Look, they've got to be 6, 7 and 8 in some order, just looking at box 4. So there's no 6 here, there's no 8 here. We don't know about this one. 9 can't go there. 6 can't go here. 7 is in one of those two cells. Sorry, you can see I'm floundering now. We've got a 1. Where does 5 go? Yeah, 5 is placeable in box 3. It must go there. We can remove 5 from here. It's incredible how this puzzle, I mean, maybe I'm missing something, but it's still holding out resolutely, isn't it? So 5 now is in one of those 3 cells. It's definitely, I mean, it really isn't easy, this. It really is not easy. This 10 cage, look, it can't be 4, 6, and it can't include a 9. So this 10 cage is either 2, 8 or 3, 7. Right, okay, now this is not an easy trick, but look, we have a 7, 8 here, and either there must be a 7 or an 8 in one of those two cells. So there is a virtual 7, 8 pair in those 3 squares, which matters because this square therefore can't possibly be a 7. If this was a 7, this would be an 8, and then there'd be no way of filling this 10 cage. So this is a 5. This is a 7. Therefore, this is a 6. Look, that gives us another digit at least. Oh, yeah, this is nice. 6 is now forced not to be in the 22 cage. Now, once we know that, we know the 22 cage... In fact, that can't be a 9, look. Oh, in fact, we could have got this 9 before. That can be a 9. That's a 4. Let's just check whether that did anything that would have... That would have given me a 4 here, relatively simply, look. Gives me a 4 here. Allows me to eliminate some 4s over there. But I think the point still stands. Now, once we get the 6 locked outside the 22 cage, we now know that this 22 cage must be made up of 5, 9 and 8. And you can see I've got a 5, 9 pair in it. So this must be an 8. No 8 here. This must be a 7. 4, 8 here. So this is an 8. That gives me an 8 here. This must be a 3, 7 pair. That means that we get the 8 and the 7 here. This is not, this is not 3, but more importantly, that square's a 2. 1, 3, 1, 2, 3. Don't break. Please do not break. This is 1. That means that's 3. This is 2. I think it's still looking okay. Let's delete that and make sure it's clear this is a 5-9 pair. You can see this square, unless I've made a big boo-boo, needs to be a 2. That looks okay. 2, 2 get fixed here. Oh, 1, 3 pair in box 3. So that square's got to be a 2. That's not 2, which means this square is a 2. One, 3, 4, 8. This is not 4. Not 4. I want to remove the 4. There's a 1, 5 pair, so the 4 must go there. Good grief. So let's come back over here then. We've not put 1 into this box yet, so this is a 1, 6 pair. And where's the final bit that's going to crack the puzzle open? Where are you? I don't know. It must be here. It must be staring me in the face. This is going to be so annoying if I grind to a halt now after 51 minutes of solving. Where is the trick? So in fact, look at this row. It's this 7, isn't it? Yeah, of course it is. That's 7, and that 9, and that 9, and that 5, and that 5, and that 1, and that 3, and that 1, and that 1, and that 6, and that 6, and that 3, and that 3, and that 7, and that feels better. This 1 figures the 1 and the 4 out. So let's delete these and actually see what we've got to place. We've got to place a 3 or an 8 into this square from the column. There's an 8 over there. So this should be a 3. That fixes the 3 and the 2, fixes the 8 here. This square's a 2. The 8 and the 4 get resolved. I need to put a 4 in this box. I need to put 8s and 3s into this box. And Phistomefel, I have finally completed your Cloverleaf puzzle, I think. Check. Yes, I got it. Not easy. I hope you will agree with me about that. Now, as usual, there may be things that I've missed there. I feel like I could have done more with this earlier. And it could be that I focused on I focused very heavily on this row and its impact on these cells down here. But perhaps if I'd looked at, I don't know, this column or this column, I would have found a more straightforward path. So do let me know in the comments. I do read them. I do really appreciate them. And yeah, thanks for watching, and we'll be back later with another edition of Cracking the Cryptic.